So in this video, we're going to talk about the idea of Sn1 Reaction Basics, some examples, and obviously the whole scenario around Sn1 reaction. We covered Sn2 Reaction Basics, so go ahead and take a look at that video, and obviously then we have some practice questions that you would actually see on an exam to kind of differentiate between the two, as well as E1 and E2 reactions. Now, Sn1 reaction, conversely to that of Sn2 reactions, it is actually unimolecular. Right? Now the 1 stands for the idea that it follows first order kinetics. The N, no surprise, stands for the idea that it's a nucleophilic reaction. And the S, as to no surprise again, stands for the idea that we're dealing with a substitution. So if it's unimolecular, what we're really saying with respect to the rate law is that the rate is equal to some constant K times only the concentration of the alkyl halide in this case. Now, what are the steps in an Sn1 reaction? There's two steps. You have a slow step and a fast step. So step number 1 is the idea that we have some sort of formation of a carbocation. Right? So the first step in the Sn1 reaction is that we have a formation of a carbocation. So here R is going to represent anything, X is our alkyl halide, and essentially the bond is broken to put the electrons in the form of lone pairs on the alkyl halide. So that gives us an R that's now positive. In this case, that's really representing our carbocation plus our X, which is now negative. So R again is our carbocation. The second step in reaction, which is the fast step, and this is step number 2, is the idea that the nucleophile attacks the carbocation. So that's the second step, which is the fast step, right? So we have R plus, which is a carbocation. We take a nucleophile, and we get an R nucleophile. So that is the fast step. So let's write this down, that this is the idea of the slow step, or step number 1, formation of carbocation, or step number 2 is the fast step. So let's look at an example. If you're given this molecule on an exam, the slow step, which is in equilibrium, says that we form the carbocation. So in other words, we get this as a product. Carbon now has 3 bonds with a plus charge, plus the iodine in solution as a minus. Right, so that is the slow step. In other words, this is the slow step, formation of the carbocation. Now we could take this carbocation and we could react this with a nucleophile. In this case, I'm going to use methanol, where the lone pairs on the oxygen will act as a nucleophile. And we're going to say this is the fast step. And this attacks the carbocation. And essentially, we get something that looks like this. There's our methyl group, nothing changes. Now we have an oxygen that has a hydrogen and a CH3 on it. Now you should notice that here's my iodine, it's still in solution, it's negatively charged, but oxygen with 3 bonds has a positive charge. So notice that we're also conserving charge as well. And the last step, and this is kind of a mechanism, but in the last step of the reaction, what we really have is the oxygen again, 3 bonds, 2 lone pairs, it's a positive charge. There's our hydrogen, there's our lone pairs, there's our there's our positive charge. And the last step, or this is still the last step, but it's really the mechanism. We have one more molecule of methanol, that comes in and acts as a base, take off the hydrogen next to it, and put the electrons in the form of lone pairs on the oxygen. So use methanol and water, and essentially what we get is this as the product. So when all the way from this is the reactant to the encircled product down below. Now notice again we have a fast step and a slow step. Okay? So let's talk a little bit more about what we should know in general about the Sn1 reaction. If you look at an energy reaction diagram like we did for an Sn2 reaction, and energy is on the y-axis, reaction progress on the x-axis, we actually see that the reaction progresses in kind of two states. Here's transition state 1, transition state 2. The first step is actually the formation again of the carbocation. Right? So carbocation forms. And so if we look at the example above, this would be that first step. Second step is where we have the attack by the nucleophile essentially, right? And this is the fast. Right? Formation of a carbocation, like we said before, is the slow step. Right? Now let's talk really about carbocation stability. This is an important concept. Remember we said that in the Sn2 video, we said that never do Sn2 chemistry on a tertiary alkyl halide. With respect to carbocation stability, a tertiary carbocation is way more stable than the secondary carbocation, which is more stable than a primary carbocation, which is way more stable than a methyl carbocation. Now here's what I want you to take away. Never do Sn1. So never do Sn1 chemistry on a primary or a methyl carbocation. Right, so just remember that. Never do Sn1 chemistry on a primary or a methyl alkyl halide. The solvents for Sn1 reactions, remember we said that Sn2 reaction we use polar aprotic solvents. For Sn1 reaction is the opposite, so we use what we call polar protic solvents. Alright, so these are solvents that has some sort of hydrogen attached, like NH or OH compounds. So we say polar protic solvents are best for Sn1 reactions. Now before I let you go, we have to talk about two different things, which is really weird with Sn1 reactions, but you need to know this. If I have this molecule as an example, there's my bromine, there's my alkyl halide. If I want to do Sn1 chemistry on this molecule, first thing is going to happen is a slow step. So the bromine is going to leave. And in the intermediate, what I really have is something that looks like this. I have a carbon that has one hydrogen, right? And let me write it out explicitly, right? Because remember, essentially, we still had one hydrogen here. I just didn't write it in, right? So at this point, I'm actually looking at a secondary carbocation. But remember, we said that a tertiary carbocation is actually the most stable. And this is where things get weird. We actually have what we call a 1,2 hydride shift. Now this happens if you have an available hydrogen on the adjacent carbon, and if this is possible, then I'm able to get the carbocation and on a more stable carbon. So in this case, what really happens is something weird happens. This hydrogen comes and satisfy the positive charge on the secondary carbocation. Now essentially what that did, or essentially what that does is that now I have this as the product, or not the product, but this as the resultant product of the 1,2 hydride shift. Notice that my carbocation moved from this carbon to this carbon. Now the carbon that, let me see, that's in yellow that we're pointing at, this is now a tertiary carbocation, right? In other words, there is no hydrogens. Remember, we spoke about carbocation, and the idea is that if there's no hydrogens, that's a tertiary carbocation. If there's one hydrogen, that's a secondary. If there's two hydrogens, that's a primary carbocation, right? So we moved from a secondary carbocation to a tertiary carbocation, and this tertiary carbocation is where our nucleophile will now attack. So essentially the product of this reaction will be this. You need to understand this because this is very important when you're doing reactions on your exam. Notice that where the alkyl halide started, it's not where the substitution or where the nucleophile is at. Now this does not always happen, right? You have to make sure you have, if you could do a 1,2 hydride shift, it's beneficial in that I'm going to move to a more stable carbocation. Let's look at one more. What if you're given this molecule? And okay, well, this is going to Sn1 chemistry. Well, the first thing is going to happen is a slow step. So the iodine is going to leave. That's going to give me a secondary carbocation, right? Again, one hydrogen. The hydrogen was here, I didn't write it. Now, obviously, I have the iodine solution that's negative, so that's preserving my charges. Now, we just spoke about 1,2 hydride shift, but here's something also weirdly occurs. This is what we call a 1,2 methyl shift. And it's the idea that if I have a methyl groups in excess on an adjacent carbon, it actually moves and satisfies the positive charge on the secondary carbocation. So essentially, as a result, and maybe I should write this in. So essentially, as a result, what I have is that on this carbon, now I have a hydrogen and a methyl group, where on the carbon adjacent to it, the plus charge is there. Now remember, we said that this was a secondary carbocation, and now we've moved the charge to a tertiary carbocation. Again, no hydrogens. Right? Now again, the last step is that the nucleophile attacks. It's going to attack the positive charge, or in other words, the carbocation, and essentially my product should be this. Now, in organic chemistry, especially for where you're at right now, we only have, right, so write this, we only have methyl and hydride shifts. So only methyl and hydride shifts. Again, notice that it is beneficial. I'm moving the carbocation to a more stable carbon. So let's do one more example before we wrap it up. If I have this molecule, or in other words, I really just did this problem, but again, all I'm doing is replacing the nucleophile here with water. So it's still the same molecule. I have the positive. I'm just finishing up. Instead of using a nucleophile and I'm using H2O as a nucleophile. So this is the same situation above, but instead I'm using water as a nucleophile. Again, oxygen has lone pairs on it, so it will attack. Essentially, this is bonded to an oxygen that has two hydrogens, pair of lone pairs. So this has a positive charge, And in the last step, I have water now coming in. Again, another molecule of water acting as a base now. Take off the hydrogen, put the lone pairs on the oxygen in the form. Put the bonds in the form of lone pair on the oxygen, and we get the product. So it's the same product above. The only thing is that I replaced Nu with OH as a nucleophile, and there goes our hydrogen. This is our methyl group. So that is Sn1 reaction in a nutshell.